Hi, everyone. Thank you for joining our webinar today titled Introduction to Dynamic Light Scattering, DLS. With me is Dr. Jeff Bodycomb.
Hi, how you doing?
Very good, very good. So he is our product line manager for particle characterization. He's got his PhD in material science and engineering. He's got years of experience on dynamic light scattering, laser diffraction imaging, nanoparticle tracking, and so many more. So he's especially interested in, sources of error measurements, scattering techniques, and you'll probably see his footprint everywhere in terms of literature or marketing collaterals. My name is Julie Chenwin. I will be your facilitator today, and I'll be monitoring any questions and comments in the background. And I'm going to pass the ball to Jeff.
Okay, great. Yeah, so today's presentation is Introduction to Dynamic Light Scattering, and we're going to kind of get ourselves started on a pretty popular nanoparticle characterization technique. I'm Jeff Bodycomb. I'm with HORIBA Scientific, and I'm actually coming to you from our office and factory in New Jersey. Quick outline, I'll give an introduction, okay, give us a little perspective about what I want to talk about, move into the meat of the topic, which is what is dynamic light scattering, what does it measure, and then I'll wrap up with some comments on method development and using the technique. So dynamic light scattering really refers to measurement interpretation of scattering data on a very short time scale, microseconds. And you'll use it to determine particle molecular size, size distribution, and relaxations in complex fluids. So that's the gist of the topic. But we ought to put some perspective around it. There are other light scattering techniques that are fairly popular. The first is static light scattering, which you hear expressed as laser diffraction quite often in the particle area. And then it's also used for polymer analysis. And that's over a longer time scale. You're looking at scattering over, say, a second or so. You're not really looking at how the particles move, but just how they scatter. Electrophoretic light scattering, that's using scattering to track particle motion in response to an applied field. And I noticed Julie put up one of our handouts on zeta potential determination, and that's really where electrophoretic light scattering is primarily used. And finally, nanoparticle tracking analysis is another scattering technique where we're going to look at particle location and particle motion like DLS, but with a video camera. And so that gets us some benefits as well as some drawbacks. This is kind of one of my favorite slides, or a flavor of it, where I plot resolution on the left axis and particle diameter on the bottom axis, and list up a range of techniques. And so you're up in the millimeter range, you're looking at things like image analysis. We're basically taking pictures of particles. As you move down into the submicron, this below 10 to the 0 to the center, you'll start looking at centrifugation, nanoparticle tracking, a bit of laser diffraction, and then our friend dynamic light scattering, which, as you can see by this plot, reaches down to the smallest particle sizes. It also has the lowest resolution for components of a mixture. So anyway, this is a handy thing to have as you start thinking about different particle characterization techniques. Gives you a quick shortcut to what your options are. So I mentioned laser diffraction. I'll call it 1.5 times. The first time was, of course, as another scattering technique, as static light scattering, and the second is in that graph that I just showed you. Here we're looking at scattering as a function of angle. So you have a light source coming in from the right, hit the sample, you have detectors at multiple angles, and you use that to find size and size distribution from tens of nanometers up to millimeters. It's very fast, it's very repeatable, and with the wide size range, ability to work with a wide range of samples, it's probably one of the most common particle characterization techniques out there. Here's some example data, and these can both be done on the same tool with somewhat different sample presentation. On the left, I have a silica suspension at 30 nanometers, And on the right, I have size distributions of coffee powder starting at about 300 micron up to 1 millimeter, so much larger sizes. And the one on the right, of course, is a dry powder. One on the left is a suspension in a liquid. So that's a testament to kind of the range and power of laser diffraction. A second technique is nanoparticle tracking analysis, where we use, in the modern implementations, multiple simultaneous light sources to illuminate a sample, and then look at the scattering with a video camera. And when you do that, you can watch the individual particles move around by Brownian motion, and from that extract the size of each individual particle. This will get you better resolution, and it will also particle concentration. So that's kind of the neighborhood we're working in for analysis. And now I want to move into what the meat of the things. What is dynamic light scattering and what does it measure? So I mentioned the optics briefly. I'm going to go through them again. You have a laser, this case coming on the left. You shine it on the particles. And then we're going to look at scattering at a single angle. Now, you can put multiple detectors in the same instrument. So you'll have a 90-degree for right angle scattering, might have a backscatter detector as well. And you don't tend to like to go to forward angles because the data just isn't very good. You're going to have a signal that is going to be random. Just look at random noise, random fluctuations in the scattering with time, and that's what you're going to interpret to determine particle size. And that random signal is really coming from particle motion. So when you have particles in suspension, they're going to undergo Brownian motion. It's random thermal motion, which is related to the particle size, the liquid viscosity, and the temperature. And you really have thermal energy driving the particle motion, and you have viscous drag slowing it down. And so the balance between these two gets you your diffusion coefficient, and you can relate that back to the particle size, which appears in the viscous drag term. So how do we get a random signal from that? Well, if you think about two particles, which I show on the left, you have a beam of light coming in, and then you have scattering from each of these two particles, and we're going to sum the scattering at the detector. And if this difference in the path of the light between the first particle and the second particle is about half a wavelength, then the scattered light will interfere and you'll have almost no signal. And so you'll have a very weak signal. Now you wait a short period, these particles will start to move with respect to each other. And that is this center image where I have the dashed lines with the original positions, and I've just moved the particles a little bit. So now the scattered light is exactly in phase. I get twice the signal. So this motion wants to be random motion for dynamic light scattering. So you can't really put up with bulk flow in most cases. I'll complain about selling later on, but you really just want that random thermal motion. So if they're randomly moving and the light is randomly going in and out of phase, I should say the sum of the scatter light is going in and out of phase, you will have random fluctuations in your scatter intensity. And so that's the root of why you see this sort of signal. Now, it's random, but it doesn't mean it's free of information. And so we're going to interpret these fluctuations in terms of what's called an autocorrelation function. The math is shown here. My take home from this is that you're going to have an exponential decay. So at very, very short time scales, let's go back a slide, these particles have not had a chance to move at all with respect to each other. So your signal doesn't really change that much. As you wait for a very, very long time, then the particles back here have had a chance to move every which way with respect to each other. And so the intensity at some long time is not as related to the intensity of starting time compared to the intensities of very short delay time. So long and short really is going to depend on particle size. if you have very small nanoparticles and they diffuse quite quickly, these autocorrelation functions decay very quickly. If you have very large particles and they're moving very slowly or diffusing very slowly, then you're going to see those fluctuations persist for a longer period. So I'm going to take that decay constant from the previous slide, and I'm going to turn it into what's called mutual diffusion coefficient. So the decay constant gamma is diffusion coefficient times the scattering vector squared, and that's a way to express the scattering angle and the wavelength in one compact place. And I will have this equation, which is pretty close to the Stokes-Einstein relationship, where you'll have the thermal energy on top and the viscous drag on the bottom. And your hydrodynamic size just jumps right out of that equation for you. I'm going to circle the viscosity term because when you do dynamic light scattering, that's probably the most important term or practical term in measurement, because viscosity is a stiff function of temperature. And so all modern instruments have temperature control so that you will know the viscosity of the liquid and therefore extract more accurate diameter size results. I wrote a DH in there and called it diameter without commenting on why the H, but that's pretty important. So the question is, what is this hydrodynamic size that you're determining by dynamic light scattering? This is really the diameter of a sphere or that moves or diffuses in the same manner as your sample. So if you have a core shell particle, like I show on the far left, the hydrodynamic size is the size of the entire object, not just say metallic core and a polymer brush shell. You'll see the entire thing. If your particles are very small and they're stuck together, either very firmly through some chemistry or even a loose flock, you will see that the particle size is the size of that aggregate stuck together. You're not looking at the individual parts of the particle so much as the whole particle in one piece. And finally, if your particle is not spherical, we're just going to pretend it is a sphere. So if you have something that's football shaped or tubular, we're going to obtain a hydrodynamic size that is a reflection of how that overall particle moves. And it's nothing quite so convenient as the minor or major diameter of ellipsoid, for example. It's some combination of the two. So quick comment on hydrodynamic size. Here's some data with gold colloids from NIST. And if you look at the sizes by AFM and electron microscopy, you see from about 8.5 to 9 nanometers. But the dynamic light scattering size is 13.5 nanometers. So it's quite a bit bigger, these same particles, when measured by DLS compared to these electron microscopy techniques. And that extra size is really that core gold particle along with the citrate shell that is being used to stabilize the particle in suspension. The reason you don't find this 13 nanometers back in those electron microscopy measurements is that the microscopy is going to depend on the difference in electron density. Electron density of gold is quite high, and you may not even notice that there's really any sort of shell around this particle. So here we're looking at SEM up here and TM. At TM, you see the gold there very nicely, but you don't see what's on the outside. With DLS, you can see that. And that certainly is an advantage in a lot of cases, but it's important to keep this in mind as you're interpreting data or you're trying to reconcile results between different techniques. So here's some repeatability data with Nanogold. And here I plot the autocorrelation function as a function of delay time. And I've put the delay time on a log scale. We can probe a very wide range of delay times in a dynamic light scattering instrument, which is quite convenient and gives us a wide range of sizes we can analyze. To stuff it all into a graph we can look at, we make it this semi-log plot, and you often see these backwards S shapes. So from kind of where it sits down, that's gives you a sense of the size if you're used to your instrument, or you let the software do it for you. That's the most popular technique. And then make 6 repeated runs, about 50 nanometers, average standard deviation of 0.9, and a coefficient of variation of 1.7%. And so this gets to something that's quite nice about dynamic light scattering. Actually, one thing's written here and the other isn't. The first is that each measurement was probably only about 2 minutes, so it's very quick. The second is that for the overall average, it was quite repeatable because I had a nice stable sample. So you have nice, fast, repeatable results. Now, I showed you 50 nanometer gold, and let's look at some 10 nanometer gold. And so I have the autocorrelation function of 50 nanometer gold at the top, the 10 nanometer gold at the bottom. And you can see as I go to smaller particle sizes, the autocorrelation function kind of sits down at shorter delay times, which is an indication that it takes less time for the relative positions of the particles to just move about any which way compared to each other. Again, I have 5 repeats, average of 10.4 nanometers, standard deviation of 0.2, coefficient of variation of 1.9%. And so this is quite happy. These are clean samples, and with good samples, you can get this kind of performance out of DLS quite often. So here's some comparisons between 2 different labs with colloidal silica. This is at 34.5 nanometers. The Z-average size, I'll get to that in a moment, what I mean by Z-average, of 34.4 versus 34.6. So my laboratory to laboratory performance can be quite good with dynamic light scattering. Another example of data, polystyrene latex. So this is the latex standard. Again, with a narrow size distribution, my obtained size matches expectations. This was a 4-minute measurement, which is about 4 times longer than it needs to be. Anyway, we're pretty happy with that. So that's great. I've showed you some examples and just talked about what to do if all the particles are the same size. And in truth, the vast majority of particle samples have a range of particle sizes. So what's going on? Well, let's look at these autocorrelation functions. And on the left, I have a series of graphs with the delay time on the linear axis. On the right, it's the same data on a log scale. So your large particles has a very slow decay in the green. Your small particles will have a very fast decay. And if you have a mixture, you would simply take the sum of the autocorrelation functions for each particle size, weighted by the scattering power of the particles in each size class. And so your mixture, you'll see it's distorted compared to the nice, neat exponential decays shown in the top 2 plots. Well, how do you treat that? There are 2 ways. The most robust is something known as cumulants, where rather than treat this exponential decay with a single decay constant, we're going to expand this out as a power series. So you still have your friend gamma, and then you'll have a second order term, so gamma delay time tau, second order term that goes with tau squared, and so on out. So this gamma bar, you can then turn into an average diffusion coefficient, which you can then use Stokes-Einstein to get yourself what's called a Z-average hydrodynamic size. Quick warning, this is different from the Z-average you encounter in molecular weight analysis and Zim plots. So somewhat different weighting. The Z comes because there's some similarities philosophically, I guess. That second order term, you can divide by the square of your gamma bar to get a polydispersity index, which tells you about the width of the size distribution. So the cumulants technique works reasonably well for for more realistic samples. And we can now talk about 2 measures of your sample, your Z average as an average size, and the width of the distribution as the polydispersity. So question, what do we mean by Z average? Well, you work through some math, and the Z average comes out to be the intensity-weighted harmonic mean size. And the harmonic mean really means I have 1 over the mean is sum of 1 over each size in the sample. And then I weight by scattering, not by the number of particles in each. So here's an example plot where I have in blue the volume weighted size distribution, and then in green the intensity weighted size distribution. So what I've done is just with math taken all these particles and said, well, gee, at 50 nanometers that scatters pretty weakly, so the total scattering is fairly small. But up here at 200 nanometers, the scattering is quite strong, and so the scattering effect is stronger. So I have lots and lots of scattering from these larger particles. That shifts that whole distribution to the right, and that is the distribution used effectively when you report out the Z average size. I also indicate that the harmonic mean diameter is different than, say, a volume-weighted mean diameter, which will be, in this case, to the right. Long-winded explanation. The way most people use this in practice is note that, hey, I can get a nice reliable value for Z average size. As my size goes up, so does my Z average size. Let's just do our reporting around that and watch my particles get big or get small. So here's some example data for silica. This is quite a bit larger than the previous example, where 4 repeats at about 480 nanometers. And you notice that all these are quite closely grouped. So I think with 480, the one furthest away at 473 or 487. So it's within a couple percent. I also have in the table the polydispersity index with an average value of 0.08. And you'll notice that the polydispersity index tends to vary more than Z average diameter. And that kind of makes sense that kind of measures of distribution width have a higher uncertainty with the data set than measures of central tendency. Also, something to keep in mind as you're watching your data is you expect your polydispersity to vary more than your overall average size. Well, if you stare at the math for a while, or you say, just remember what I said about how we're simply adding up exponential decays, you think, well, gee, I have this autocorrelation function, and I know it's a sum of these exponential decays. I can do a bit of math and extract a value known as electric field autocorrelation, and that is just to integrate over the exponential decay e to minus gamma tau, and the intensity for each gamma, and each gamma will correspond to a different size class. Like getting G1 looks pretty straightforward. I can just measure C. You can realize that your value of beta can be almost ignored. Well, it's pretty easy to figure out what beta is. Maybe that's the best way to put it. And I've extract G1. Great. So now I have these sum of exponential decays. I can solve for S at gamma and get a size distribution. A quick caution, that is what's known to mathematicians as an ill-posed problem, which means that for a finite data set, there are actually an infinite number of size distributions that will fit your measured data set. And it doesn't matter how many channels your correlator has, you're going to hit this mathematical wall. Now, in practice, we have a few things that we'll do to get through the day. The first is that we're going to just ignore all the possible size distributions that involve negative particles, and that helps a lot because a lot of these infinite data sets or infinite size distributions have negative particles. They oscillate. The second thing we're going to do is feed a little bit of information into the math about what we think about the size distribution. And different manufacturers approach this in different ways, and how much you're allowed to touch this fitting procedure. Let's take a bimodal sample And let's start with 2 buckets of particles. I have my green bucket with 20 nanometer latex and my blue bucket with 500 nanometer latex. And I run each individually. Now, if you remember the earlier measurements where I had very tight repeatability, you probably figure out pretty quickly that, hey, if I have a bucket of 20 nanometer and a bucket of 25 nanometer latex, I could differentiate between those buckets quite readily. And in truth, you can really do that with DLS. Now here, I'm taking these two. I can, of course, even more easily differentiate between 20 and 500. Now let's dump them both into the same bucket, make a measurement of this mixture, and now you have the results shown in black. So I have a nice peak, still pretty close to 20 nanometers, and another nice peak, still pretty close to the 500 nanometers. And so I can resolve these two well-separated size distributions. And so that's something you can do with dynamic light scattering with well-separated particle sizes, with kind of the numerical cautions I gave you before. The caution I haven't added is that if you have very closely spaced peaks, they will tend to merge into one. So those are the ways you'll analyze your data. You can make a measurement. You'll have the overall Z-average size. You will have a polydispersity index, and you can extract out a size distribution. It is a chromatography, but you do get some information about the size distribution. So what are some example data? This is Ludox, and I want to say it's TM50. So this is a colloidal silica used to clarify various drinks. So there are vast quantities of it used for all sorts of things. And this kind of matches the data from the LA960 laser diffraction, have nice size distribution. Classic example. Another example application is that if you're looking at protein aggregation, so this is BSA, which does tend to aggregate, and you can measure it and watch the Z-average size kind of float up as you see dimerization and so on take place with BSA or any other protein. So if you're evaluating protein systems and you want to see if you really have protein monomer in solution, dynamic light scattering is really a great tool for that. Here's another example where we're looking at 10 mg per ml lysozyme at pH 2. And this was but deliberately not a particularly stable system. And we looked at the measured size. Lisa Cole and Ben Burnett at FIT looked at measured size as a function of time. And over time, you could watch the size start, and then once the lysozyme degraded or unfolded sufficiently, it would start to aggregate. And so here was about 120 hours or so. Your other kind of experiment to do is to start heating proteins and look at particle size, which will get you, which will tell you what temperature they start to unfold. This kind of analysis can also be done with a view sizer and nanoparticle tracking, particularly if you're looking at larger aggregates. Liposomes are emulsions that show up a lot in drug formulations. You can use them as a drug carrier. You'll see them as adjuvants for vaccines. And the size is critical to really how you encapsulate your proteins if you're using it as a protein drug carrier, how it affects functions within the body, how it is stable over time, and then of course any drug product delivery. So if you have a very broad size distribution, you can have something known as Ostwald ripening, where your large particles will grow at the expense of the small particles in order to minimize free energy. And so you like narrow size distributions. Finally, so those are kind of walk through what is dynamic light scattering and some possible measurements. One I don't have a graph for, although I showed it to you briefly, was I showed polystyrene latex. Dynamic light scattering is a method of choice for characterizing latex or emulsion type polymerizations, and not just the latex stearins with a narrow size distribution, but also when you're manufacturing latexes with broader size distributions, and you're not just standards. I kind of want to wrap up with some comments on method development and what you might encounter and what you might want to think about. So, dust. So, as you get into nanoparticle work, dust is your big enemy. These are large particles compared to nanoparticles, so they tend to give you nice, strong signals. They're rare. There are not very many of them, and I say that almost by definition because if there are a lot of dust particles in your sample, that's part of your sample. If you have a few particles falling from the air, that's rare. You cannot get good statistics of a small number of particles in your system, and so they give you experimental fits. Generally, they also distract from the particles you're trying to analyze. And so you want to spend some time and effort making sure that you work in a clean environment, that your liquids and so on are clean. So you will find out that filters are your friend. And I often travel around with a selection of filters for different liquids and with different pore sizes. What I do with them, I use them to remove dust. So I get a sample and I want to dilute it further. I often find myself filtering the diluent. These days it's less often because you have so many clean, filtration sterilization has really helped a lot, I guess is the way to summarize it. But you may need to filter your diluent through a 0.1 micron filter. If you have very small particles, you might filter the entire sample through a filter and just knock out the largest particles. So for polymer work, for example, you might filter your polymer solution through a 0.2 or 0.1 micron filter, so you're just looking at your polymer molecules. You can also play the same game with proteins. You have filters with pore sizes ranging from about 20 nanometers to several microns and up. A quick caution, if your particle size is expected to be 100 nanometers, you probably don't want to use a 20 nanometer filter or you will have no sample left. You can also occasionally run the cases where particles just like to stick to filter surfaces. Another approach is to centrifuge the sample and extract the supernatant for analysis. And so that would, just a short time in a centrifuge to get the largest particles out and draw off the small particles in their supernatant. Okay, suspension liquids. And I'll start with easy comments. You want to choose a liquid that does not dissolve the particles. That's easy. Prevents loose agglomerates. That can be trickier. So if you have particles that like to stick to each other because they want to minimize surface area, you're going to have trouble making measurements because you're going to measure those agglomerates. And that's where you're going to start looking at adding surfactants or changing liquids. You may decide you need to add energy to break up loose agglomerates, either with stirring, if you're lucky, or shaking. And if you're less lucky and you need to add more energy, you might use ultrasound. So to suppress agglomeration, and to bring things into suspension, you might find yourself using surfactants. First, you want to pick something that enables wetting. And that can be everything from making a paste in alcohol and then dropping that paste into water so the alcohol wets to displace the air, then put the whole mess into water, and the water can get to the particle surface. The second is to prevent agglomeration. And common concentrations are 0.01 to 0.1 weight percent, and you're looking at things like tetrasodium pyrophosphate, Triton X, on sodium dilysyl sulfate. On a bad day, I might use soap, like dish soap, but that's typically a bad day. I like to carry a few surfactants with me or hope that people have some surfactants in their lab. As you're looking for surfactants or liquids, remember Google is your friend, and you can look and see what others have done to make the same measurements. So you want to find other people or other work on particles with the same surface. That can save you a lot of time. If you don't know exactly which way to go, you can start making tests in jars. And here I have 2 liquids, and left was water. I think the right was sodium dialysyl sulfate. Um, and I put a drop of particles on the top. And these are very, very small particles, and they won't break through the surface tension. And so the particles are small enough and the density is low enough that gravity isn't that important, but surface tension is important. We're not breaking through the surface tension. That tells me that we're not wetting the particles. I do the same thing into the surfactant solution, and you can see the particles fall through as a plume. And so with a test like this, you can evaluate a number of different surfactant strategies just by eye. The tricky bit here is putting a small enough bit of sample onto the liquid that it doesn't just burst through the surface tension of the water. So you don't want to drop from a huge height or take a giant spoon of material. Moving on, comment on solvents. Of course, water is very easy, and so I like working with it. You can use glass cells. Dynamic light scattering is pretty happy with most solvents because you use glass cells or quartz cells as well as plastic cells. And you can move to less polar solvents such as isopropyl alcohol or tetrahydrofuran or toluene, depending on what you know about your sample. I've mentioned polymers a few times. I should add the comment that in dynamic light scattering, we really, when we analyze polymers, it's very much like particle analysis. And so you can prepare a polymer solution and see your coil size, hydrodynamic size of the coil with dynamic light scattering. It's a pretty classic experiment. And so you can track all sorts of things about polymers this way. You are going to be working with organic solvents. And a final warning, we don't use much volume. The largest sample cell on the SC100 needs about 1 ml of liquid. So you don't need more than, say, 2 ml of a solvent at a time, but organic solvents do present fire and health hazards. As long as you're aware of them, they can be pretty readily mitigated. So if you come up with a sample and you just don't know what to do, then you're going to may need to go back and try a series of suspensions and check them by eye. So you line up a series of jars with solutions of each of your favorite surfactants and do that eye test I mentioned earlier and see which liquids wet the particles most readily, and then go back and start doing measurements with that. So now I've got my material into suspension. I've probably measured a couple times to make sure I get the same answer at some concentration. And we want to know, hey, how much material do I need? The first step is to estimate concentration by eye. And so if you're working, just getting started, you need to start somewhere. You want to have it clear enough that you can read a newspaper through it, or read your cell phone through the suspension. And so here is a series of suspensions, and you can see the best range, which is something we measured for this particular suspension, was from pretty much clear to slightly cloudy. This one on the right side was more opaque than I would have guessed, but hey, data is show what the data looks like. But these three in the middle, and particularly this one in the middle here, it's a bit cloudy, but you can still read through it. And so that's a good starting place for your material concentration. And quite often I wind up working here or here. Want to dial in the method, and this is going to happen particularly if you're looking at QC, you want to do something over and over again. You might make a plot like this: measured size on the left, so Z average diameter, as a function of particle concentration or 1/4 dilution. And you'll see that you have very noisy results if there are too few particles. As you increase concentration, you have a nice flat spot. Okay, that's great. We want to operate in this decade from 10 to 100 ppm. And you'll see the results shift as your concentration gets too high. Notice I'm using a log scale here. And so one of the nice things about dynamic light scattering is that we can operate over a very broad concentration range and still get reasonably good results. Now, I want to make a comment on salt concentration because, okay, so this is colloidal silica, and I'm plotting measured size as a function of particle concentration, and I dilute it in DI water in red and in 10 millimolar sodium chloride in blue. Now, the interesting thing about this is, first, it shows you an important rule, which is when I talk about all the math for dynamic light scattering, I'm assuming the particles are freely diffusing. They move around, they don't affect each other. They just, or I should say there's no physical effect between the particles. If you have electrostatically charged particles like a latex, then you will have long-range interactions, and that will affect particle motion. And so you can suppress that by adding an electrolyte, in this case 10 millimolar sodium chloride. And what you can see in this plot is that just by turning off the long-range interactions, so I've changed nothing about the optics of this sample. I've just changed kind of the effective concentration. I obtain much more consistent and more accurate size results compared to having strong interactions between particles. And so this tells you, as you move to higher concentrations, what's going to get you first is often interactions between particles, much less so than any optical effects, because it's the same optical system, same concentration, light behaves the same way, it's just how the particle motion was changed. So you want to think about suppressing long-range interactions as you make measurements. So kind of a summary of hints. Start looking at how other people have measured your kinds of materials. Consider your solvent and your surfactant. You'll probably hope that water is your solvent or your liquid. Consider using ultrasound. Expect to be filtering at some point. Choose the largest sample cell you can. I didn't get into this with any pictures or anything, but there's a range of sample volumes you can use dynamic light scattering, and the smallest would be about 10 microliters. That sample cell is expensive and tough to clean. I don't like it. As you move up to the 1 ml cells, that is the least expensive and easiest to clean cell. So, there's always a trade-off. And if you optimize your particle concentration. So, comment about applicability. Not all motion is Brownian motion, and I kind of hinted at that with these long-range interactions. Another thing that comes up a lot is gravity, and so just about everybody's lab has gravity, at least all of my customers do, and that gives you a natural limit for dynamic light scattering where you have gravitational settling. As your particles get larger, gravity becomes more important, and somewhere around half a micron or so, about 1 micron or so, your Brownian motion versus your gravitational settling is comparable, and you're going to have a rough time with dynamic light scattering. In addition, your samples will start getting to the bottom of the cell fairly rapidly. So I don't like to use dynamic light scattering for very large particles. I'll often shift to laser diffraction, even if the instrument can be beaten into submission to do it. It's just a whole lot more fun to do laser diffraction. So kind of some closing comments. Dynamic light scattering can be a problem because it's very sensitive to large particles and particularly large particle impurities. And so you're going to have to filter them off. You don't have great resolution for your size distribution. You would go to a technique like centrifugation or nanoparticle tracking to resolve that. And it's not really appropriate where settling is significant, and you would go to a technique like laser diffraction that is happier with large particle sizes. Now, some advantages of dynamic light scattering, and there are a lot. A rather enjoyable technique. It's very fast. You're getting measurements in 1 to 2 minutes. It's typically faster to make a DLS measurement than speculate as to what you have. Just stuff it in the instrument and find out. How's that? Yeah, so that's just really, really convenient. It's repeatable. Uh, you have a good sample, and you have very tight repeatability, which lets you differentiate between fairly similar samples. It's non-invasive. It's very easy to get your sample back and use it for other sorts of analysis. You have fairly dilute suspensions, and this means you need only small quantities of sample. If you can get yourself, if you only need 10 microliters of liquid and your particle concentration is in the high ppm, you're using next to nothing. It's a good tool for picking up trace aggregation. Yeah, so if that's what worries you, it's a nice tool. It's really a tool of choice for macromolecular sizing. It's much more convenient than, say, a static light scattering measurement, and it reaches down to fairly small sizes. So really reaching these small particle sizes is kind of the same as a macromolecule. And so dynamic light scattering, because you're taking data from all the particles, you have a fair amount of light to work with into a single detector, you go down to the smallest particle sizes. The HORIBA implementation is the SC100, and Julie shows wisely in her handouts, because not only does it do the dynamic light scattering size, it can also have do zeta potential measurement, which she mentioned, and that's the electrophoretic light scattering, and molecular weight measurements, which she also mentioned in the handouts. So it's a flexible general purpose DLS tool, like it a lot. And kind of some closing comments about dynamic light scattering. I guess this is your take-home graph, if you will. It's fast, repeatable nanoparticle sizing. You don't want to use it over a micron, that's a nanoparticle. Not going to take you very long, that's the fast. You'll get the same answer twice. If you have a stable sample, that's repeatable. You do need to fret a bit about suspension chemistry in the method development, and that's just because nanoparticles have huge surface areas, and these chemical considerations come up much more than you see in larger particles. And your results will be with hydrodynamic size. And if you keep that in mind, that will often help you understand what the instrument is telling you about your materials. Okay, well, thank you for your attention. I guess I'll go back to the summary slide and see how we did for questions.
Well, thank you so much, Jeff. So someone commented that this is a really good webinar, not just for those people who are looking at DLS, but for new users who purchased the SC100. So good news.
Good.
Okay.
Good.
You might like this question. How do you calibrate the device from standard samples?
You've been working together too long. Yeah, so that's a great question. So dynamic light scattering relies on two things. Well, okay, measurement dynamic light scattering and the instrument relies on two things primarily, and I'll say a third thing important enough that I better mention it. So the first is the geometry of the instrument, which gets you your scattering vector. And the second is the timing inside the signal processing electronics and the autocorrelation function, okay? And those are very, very stable. I guess in 20 years, I've seen one bad correlator in my life. And that was not a HORIBA. But anyway, so you just don't expect those kinds of issues. They're very, very stable. The third thing is the temperature control on your sample, which really ties into viscosity. And if you're and the most common issue that comes up, if someone puts in a cold sample, the viscosity is higher than you expect because your system is set at, say, 25C and you put in a 12C sample. When we check an instrument out, we will calibrate in the sense of confirming instrument performance with a particle standard. And if you get the right answer, you know everything is fine. If you don't have a sample prep problem, you get the wrong answer, you're really going to have to go back and repair something in the instrument. Again, it's very rare, but it might be something in temperature control. on the system. So the calibration system is really built in when it's manufactured, and we just confirm it's still working. It's not like a microscope where you put in an artifact and you adjust a knob to get the length scale back out because it drifts with the weather. It's just going to stay there.
Thank you. The next question. This person wants to know about the detailed knowledge about DV10, DV50, DV90, and DV97. So we might need to go into a little bit about, data interpretation and all.
Okay. So what you're trying to do is look at the tails of the distribution found in dynamic light scattering. Okay, here's a distribution. You want to talk about D10, D90, D97. This is dynamic light scattering is not really a great way to get at those numbers. In fact, it's not very impressive at all. You're probably going to have to move to nanoparticle tracking analysis to get those sorts of details of size, distribution. And the underlying reason is that we're bringing all of the light into a single detector and then sorting it back out with a mathematically hazardous procedure, which gets you some great benefits, but D97 and D90 are not two of them. And so you really want to do your analysis particle by particle, either with nanoparticle tracking or separation centrifugation, depending on size range. Yeah, probably out of scope of this webinar, but those are my comments there.
Thank you. Can DLS be used to measure a degree of deflocculation of a suspension by increasing the deflocculation and measuring a changing hydrodynamic size?
Yes. Yes. Well, yes. So that is kind of the backwards version of that of the protein aggregation. So now we're going to start with a big flocculate, and you're going to watch the size go down with change in chemistry, and that would work quite readily. I'm going to kind of go into electrophoretic light scattering briefly, in that the flocculation is often electrostatic phenomena, and you may want to look at your particle charges and the zeta potential as a function of your flocculant to better understand your system as well. And that all happens in one box with the SC100. And that's a fairly common application in wastewater treatment labs, for example.
Thank you. Would DLS be a recommended technique to look at high concentration nucleation stage?
So if you have a high concentration of a small molecule, and then you're looking at the nucleation of particle growth, then yeah, I think DLS could be used for that. That's there's a little trickiness around the particle sizes of the nuclei that you're looking at, and how your solid phase is growing. So I'm going to assume you have nucleation growth, which is good news, because spinel decomposition could be a real mess in scattering. But if you have nucleation growth, when the nuclei first appear, you should see a jump in your scatter intensity. And then you'll start measuring particle sizes from even the smallest size nuclei. There's some limits. You do need to apply some sort of a model to track your process until your size range gets up to, say, nanoparticle tracking, where you can count your nuclei. But that would probably cut in a larger size. But DLS has been used for dynamics for a while. And again, the fact it reaches those very small sizes is quite handy.
Thank you. I think that 12% of biotech, biopharma, and pharma folks are, coming with lots of questions. I do want to honor everyone's time, so let me go ahead and put in our email here in the chat box. If you have more questions or questions that we haven't been able to address due to a time limit, please don't hesitate to reach out to us just by emailing us comments, questions, or any inquiries that you have. It's at labinfo@horiba.com. Okay, so is there anything else that you would like to add before I end the webinar, Jeff?
No, thanks. Thanks for your attention. And yeah, okay, thank you. Have
Cool,
a good one.
thank you so much. Thank you,
Okay,
everyone.
thank you. Bye-bye.
Bye for now.